Welcome to Naradar Academy. In this video, we are going to discuss infimum and supremum in the set of real numbers. Okay, first let us start with the definition of an upper bound of a set. Suppose S is a subset of real numbers and every element of S is less than or equal to U. Okay, that is all the elements in capital S are less than or equal to U. Then this U is called upper bound and the set is called bounded above. Okay, the element is called upper bound and the set is said to be bounded above. Okay, if the set has an upper bound, it need not be unique. It may have more than one upper bound. Okay, next one, supremum. Suppose if I have a set which is bounded above, then it will have an upper bound. No, now you collect the set of all upper bounds of the set. Okay, if the set of collection of all upper bounds of a set has a least member or smallest member, that member is called what? Least upper bound or the supremum. That is, first you are taking a set and you find the upper bound. After finding the upper bound, you take the collection of all upper bounds of the set. Among the members of the upper bounds, if there exists a smallest number, that is said to be supremum. Okay, the supremum, if it exists, will be a unique number. Okay, there cannot exist two or more supremums for a given set. So that is why we have stated it the least upper bound or the supremum of S, because it's a unique number. Okay, next one is lower bound. The same thing, suppose if I take a subset S of real numbers and every element of S is always greater than or equal to V. Okay, all the elements of this S are greater than or equal to V. In that case, V is said to be lower bound. Okay, again, this lower bound is not a unique number. The set may have one or more lower bounds and sometimes the lower bound need not exist also. Okay, so if it exists, you collect the set of all lower bounds of a set S, and if that collection has a greatest member, that greatest member is called greatest lower bound or infimum. And here also the infimum, if it exists, is a unique number. The set cannot have two or more infimums. Okay, with these definitions, let's see few examples for this. Now consider this set S equal to set of 3 and 4. Okay, so this is a set containing only two elements, 3 and 4. Now you see all the elements of this set are less than or equal to 4, no? Isn't it? 4 is the maximum element here and all the elements here are less than or equal to 4. So 4 is an upper bound. Also I can say all the elements of this set are less than or equal to 5. So 5 is again a upper bound. And 6 is also an upper bound, 7, 8, etc. So all the elements of this set are less than or equal to 4, less than or equal to 5, less than or equal to 6, less than or equal to 7, etc. and so on. So the collection, this entire collection is called collection of all upper bounds for S. Okay, and similarly, if you consider this set 3 is the smallest number, no, and I can say all the elements of this set are greater than or equal to 3. Okay, again what can I say? All the elements of this set are greater than or equal to 2. All the elements of this set are greater than or equal to 1. All the elements of this set are greater than or equal to 0 and so on. So this is the collection of upper bounds and this is the collection of lower bounds. In the collection of upper bounds, you choose the least member or smallest member. 4 is the least member here, no? So that is called least upper bound or the supremum. This is a unique value. Upper bound is not unique, but the least upper bound is unique. And in the collection of all lower bounds, you choose the greatest member. 3 is the largest number here, no? So this 3 is called what? Greatest lower bound. Okay. So this set has both infimum and supremum. So this is both bounded above and bounded below. So this set is called a bounded set. Okay. Consider the next example. S equal to the collection of 1, 1 by 2, 1 by 3, 1 by 4, etc. Look at this sequence. Here 1 is the first member. The second member is 1 by 2. 1 by 2 means what? 0 0.5. 1 by 3. 1 by 3 means what? 0 0.33. And 1 by 4 is what? 0 0.2. And so on, etc. Isn't it? So this set contains the elements from 1. That is starting from 1. It goes on reducing till 0. Can you understand? So here all the elements of this set are greater than or equal to 1. Isn't it? And again what can I say? All these elements are greater than or equal to 2. All these elements, all these elements are less than or equal to 1, all these elements are less than or equal to 2, all these elements are less than or equal to 3, and so on. So the collection of upper bounds, what can you say? 1, 2, 3, 4, etc. These are all upper bounds for this set. And what is the least member among all these upper bounds? 1. So least upper bound or supremum is equal to what? 1. Next, look at these numbers. This is a sequence 1 by n. No? So if the value of the denominator keep on increasing, it will approach to 0, isn't it? It will be going like 1 by 100, 1 by 1000, 1 by 10,000, and so on. There is no n for this. So how far you are going, it will be very much closer to 0. It will not go below 0 because only positive numbers are here. That is, starting from 1, they are moving towards 0. Okay, so 0 is the lower bound. That means all these elements are greater than or equal to 0. So again, how can you say all these elements are greater than or equal to minus 1? All these elements are greater than or equal to minus 2. All these elements are greater than or equal to minus 3, and so on. So among all the lower bounds, what is the greatest one? 0. So the greatest lower bound is equal to 0. Otherwise, it is called the infimum. Okay, next set. S is equal to pi plus 1, pi plus 1 by 2, pi plus 1 by 3, and so on, etc. This is almost similar to the previous problem only. In the previous problem, you simply have 1, 1 by 2, 1 by 3, and so on, etc. No, here you are having it with pi. The value of pi is approximately equal to 3.14. So finite number only. So 3.14 plus 1. So look at this one. 3.14 plus 0.5, 3.14 plus 0.3, and so on, etc. So if you look at this series closely, this is the greatest member. Pi plus 1 will be the greatest member. So all the elements are less than or equal to pi plus 1. And again, how can I say all these elements are less than or equal to pi by 2, all these elements are less than or equal to pi plus 3, and so on, etc. So this is the collection of all upper bounds. Among these upper bounds, the smallest member is what? This one, pi plus 1. So this is called the supremum or the least upper bound. Again, this is similar to the previous sequence only, no? So if you go on nearing infinity, how will you get pi plus 1 by n. So as n keeps on increasing, it will go nearer to 0. So all these elements are greater than or equal to pi. Pi plus 0 will be there, no? It will be approaching what? Pi plus 0. So all the elements are greater than or equal to pi. And again, what can I say? All the elements are greater than or equal to pi minus 1, pi minus 2, pi minus 3, etc. So this is the collection of all lower bounds. So among these lower bounds, the greatest value is what? Pi. Therefore, the greatest lower bound is equal to pi, and this is called the infimum. Next problem, S equal to set of all minus 1, minus 1 by 2, minus 1 by 3, minus 1 by 4, and so on, etc. This is similar to the second problem here. Okay, both are same only. Here you have in terms of positive numbers, here you have in terms of negative numbers. Okay, I will tell you one more way of finding the supremum and infimum. This is here we are studying about only real numbers, no? So you can draw the number line. You see minus 1 is the first element. What is the second element? Minus 1 by 2. That means minus 0.5. This is 0, this is minus 1. Next one is minus 1 by 3 means what? Minus 0.33 something, no? So it will be coming here. So if you plot all the points, it will be lying between these two lines. That is, this is minus 1 and this is 0, no? Only in this place all the numbers will be coming. That means these two are bounds for these two. That is minus 1 and 0 are bounds for the given set. Okay, all the elements are less than or equal to 0, isn't it? Therefore, 0 is an upper bound. And how can you say? Apart from 0, all the elements which are right hand side, which are lying on the right hand side to 0, they will also become upper bounds. Therefore, 0, 1, 2, 3, 4, all are upper bounds. So, among this, what is the least member? Least upper bound is equal to 0. Okay, and it is called the supremum. And similarly, all these elements are greater than or equal to minus 1, isn't it? Greater than or equal to minus 1, because it is coming on the right side of minus 1, no? Okay, so it is greater than or equal to minus 1. So minus 1 is a what? In minus 1 is a lower bound. And again, apart from minus 1, minus 2, minus 3, if you want to find lower bounds, you have to move on the left side of the number line. If you want to find the upper bound, you have to move right side on the number line. Okay, understand? So minus 1, minus 2, minus 3, etc. So among these lower bounds, the greatest one is what? Minus 1. So the greatest lower bound or infimum is equal to minus 1. Next one. s equal to 1 2 3 4 5 etc. This is nothing but our natural numbers, isn't it? So here 1 2 3 4 5 it goes on up to infinity, no? So we cannot find any upper bound. We cannot say these elements are less than some particular number. Yes, you cannot say like that. Therefore, this is not bounded above. But you can say it has a lower bound because all these elements are greater than or equal to 1, no? So 1 is a lower bound. Also you can say 0 is a lower bound, minus 1, minus 2 etc. All these are lower bounds. So if all these are lower bounds, what is the greatest lower bound? 1, and that is called the infimum. Okay, next set s equal to set of all minus 1, minus 2, minus 3 etc. So here what we have, negative integers. So if you have negative integers, it will go up to minus infinity, no? So you cannot say lower bound. You cannot find out any lower bound for this one because it goes up to minus infinity. Okay, therefore this is not bounded below, but it is bounded above because all these elements are less than or equal to minus 1, no? All these elements are less than or equal to minus 1, and all these elements are less than or equal to 0 1 2 etc. Therefore these are the collection of upper bounds, and among these upper bounds the least upper bound is equal to what? Minus 1. Okay, right. Next problem. S equal to 2, 3 by 2, 4 by 3 etc. up to n plus 1 by n. This is a finite sequence of numbers they have given. Just if you look closely into the set, you can identify what are the infimum and supremum for this set. See, the first number is 2, the second number is what? 1.5, and this is 1.3 and so on etc. This simply I have written as 1 plus 1 by n. Okay, right. Now you see all the numbers are lying between 1 plus 1 by n means even if you keep on moving towards this one, it will be what? It will be very close to 1 only. It will not go beyond 1, right? So all the elements are lying between 1 and 2. So 1 and 2 means what? 1 is the greatest lower bound, and least upper bound is what? 2. Sorry, I have written it as 3. It is not 3, it is 2 only. Okay, 2 is the supremum for this set, right? Okay, next problem. S equal to minus 1 2 minus 3 4 etc. minus 1 power n into n. See, here alternately you are getting one positive number and negative number, one positive number and negative number. So in that case you cannot say any upper bound. So this is neither bounded above nor bounded below. Okay, right. Next one is minus 1 plus 1 by 2 minus 1 by 3 plus 1 by 4 etc. minus 1 power n 1 by n. So here if you see the set, see all the negative numbers are there and all the positive decimals are also there. Anyway, they are lying between where? Minus 1 to plus 1, isn't it? They are lying between minus 1 to plus 1. That is, you see, look at this series. First element is minus 1. What is the second element? 1 by 2. Third element minus 1 by 3, it will come here. Fourth element 1 by 4, it will come here. Fifth element minus 1 by 5, it will be here only. So they are moving in between minus 1 and plus 1. So what can you conclude? The supremum is plus 1 and the infimum is minus 1. Directly you can write. If you draw the number line directly, you can easily write the infimum and supremum for this set. Okay. Next one is s equal to 3, 3 square, 3 cube, 3 power n etc. So if you see the sequence, you can easily find out this is not bounded above, but it is bounded below by 3, 2, 1. All are lower bounds. So among these lower bounds, what is the greatest one? 3 is the greatest lower bound. That is the infimum. Okay. Next problem, s equal to 1, 1 by 2, 1 by 2 square etc. 1 by 2 the whole power n plus etc. Sorry, etc. So what is the sequence? 1, 1 by 2 is 0.5. This is 0.5 the whole square etc. If you square or take higher powers for a decimal number, it will further reduce to a smaller number only. So all these numbers are getting reduced. So it will be around 0 only. So starting from 1, before 0 we are having this sequence. So 1 is the supremum and 0 is the infimum. Okay, right. Next problem. Next we will see some standard sets of numbers. First one is natural numbers. So natural number starts from 1, no, 1, 2, 3 etc. So there is no upper bound, therefore it is not bounded above, but it is bounded below by 1, 0, minus 1, minus 2. All these are what? Lower bounds. So among these lower bounds, which is the greatest one? Greatest lower bound is 1. Next one is whole numbers. Whole number starts from 0, 1, 2, 3 etc. So as like natural numbers, this is also not bounded above. You cannot find any number any upper bound for this set. Therefore, it is not bounded above, but it is bounded below by 0, minus 1, minus 2, etc. Therefore, greatest lower bound is equal to 0, and that is the infimum. Next one is integers. Integers means what? 0 plus or minus 1 plus or minus 2 plus or minus 3 and so on, etc. No? So, it goes up to infinity. That is from minus infinity to plus infinity, it moves on. Therefore, here also you don't have upper bound and lower bound. So, this is not a bounded set. Next one, rational numbers. Rational numbers, irrational numbers and real numbers. They are all neither bounded above nor bounded below. Okay. So, all these are not bounded sets. Next one, let's see, S equal to open interval 0, 1. In real analysis, we use this bracket for denoting open interval and we use the square brackets for denoting closed interval. What's the difference between open and closed interval? Open interval means the endpoints are not included. That is, you mark 0 to 1. So, all the numbers in between 0 and 1 are included except the endpoints. Okay. Closed interval means the endpoints are also included. Okay. So, this is the difference between the open brackets and closed brackets. So, for both of them, you see, if you write it on the real line, you can see all the numbers are greater than 0 and less than 1. Therefore, 0 is the infimum and 1 is the supremum. The same infimum supremum for closed interval also. There is no difference for these two sets. Though it may be open and closed, 0 is the infimum for both the sets and 1 is the supremum for both the sets. Okay. Right. Next problem. This is half closed interval. That is open at 0 and close at 1. That means 0 is not included but 1 is included. For this set also, see, you are having all the number elements between these two numbers. No. So, the infimum is 0 and the supremum is 1. Next one is open at 1 and closed at 0. Here also for this set also, what you have? The greatest to lower bound is 0 and the least upper bound is 1. Next, this is union of two open intervals. S is the union of 0, 1, open interval 0, 1, union with open interval 4, 5. Whatever may be the thing, all these elements are less than or equal to 5. So, 5 is the least upper bound and all these elements are greater than or equal to 0. Therefore, 0 is the what? Infimum or greatest to lower bound. That is 5 is the supremum and 0 is the infimum. Right? Okay. So, I hope you understand with all these examples what do we mean by infimum and supremum. Next one is we are going to discuss about one important property of real numbers which the other number systems, that is the natural numbers, integers, whole numbers, integers, rationals, irrationals, they do not possess. That is order completeness property. Order completeness property means every non-empty set of real numbers which is bounded above has a supremum in R. See, we have seen so many, around 20 examples we have seen, I think, right? Look at all the examples. See, whenever a set is bounded, it will have a supremum, but the supremum may or may not belong to the same set. For example, look at this example. Here, the infimum is 0, but infimum doesn't belong to set. Because here open interval, no, so the infimum is not belonging to this set. Supremum belongs to the same set. Okay, so but the infimum is not there in the set, it is lying outside the set. For this set, supremum is 1 which doesn't belong to this set. It is lying outside this set. And similarly for this set also, both infimum and supremum are lying outside this set. That is, they exist but they do not belong to S. Okay, right? If you look at the previous examples also, there may be sets which have infimum or supremum which do not lie on the set. Okay, right? Now you see, now let me look at this example. Q be the rational numbers, no, set of rational numbers. It is not order complete. Why it is not order complete? Look at this example. S be the collection of all rational numbers X whose square is less than 2. Okay, I am collecting the rational numbers whose square is less than 2. So, square means it's always positive number. So, it lies between 0 to 2 means what is the supremum and infimum for this set? Infimum is 0. The supremum is root 2. Isn't it? X square is less than 2 means what? X is less than root 2. But root 2 is an irrational number, no? So, Q, that is the rational numbers, is not order complete. That means if the set has a supremum, that supremum need not lie in Q itself. It may lie outside Q also. Okay, but this property is true for R. That is, whenever you take the real numbers, right? Both the infimum and supremum belong to what? R. So R is order complete. Here I did. Next, two important theorems we are going to discuss. One is characterization of supremum and characterization of infimum. So I am going to give outline of the proof for this theorem also. See, let S be a non-empty set of real numbers bounded above. Then a real number S is called supremum of S if and only if these two conditions hold. One is x is less than or equal to S for all x belongs to S, and for each positive real number epsilon there is a real number x belongs to S such that x is greater than S minus epsilon. So this is called characterization of supremum. This is a very important property. So what it is saying, that is, if you have small s as the supremum, then every element of the set is less than or equal to S. That is obviously true, no? If it is supremum, definitely it will be an upper bound. Therefore, all the elements will be less than or equal to S. What is second condition? X is greater than greater than S minus epsilon for at least one real number x belongs to S. I will come to this later. So let us prove the theorem. This is if and only if condition. No, first let's prove the necessary part. So let S be the supremum of the set capital S. I have to prove conditions 1 and 2 are true. Supremum means it's an upper bound. So upper bound means what? Every element of S is less than or equal to small s. Therefore, first condition is true. Then next, second condition I want to prove, no. So for that, let epsilon be a positive number. Then S minus epsilon will be definitely less than S, no. Okay. But S is the least upper bound. That means what? Any number which is less than S cannot be an upper bound. Therefore, this S minus epsilon cannot be an upper bound for this set. Okay. So it is not an upper bound means what? There exists some number which is greater than this S minus epsilon. Isn't it? So S minus epsilon is not an upper bound. That means what? There exists a number which is greater than this S minus epsilon. Therefore, second condition is also proved. Next, we are going to prove the sufficient part. In the sufficient part, we are going to assume statements 1 and 2 are true. We have to prove that particular S is the supremum. So for supremum, first we have to prove it's an upper bound. Condition 1 directly implies it is an upper bound for capital S. Next, we have to prove the second condition. For that, I am choosing a real number S dash which is less than S. S dash is smaller than S. Then S minus S dash will be greater than 0, no? That S minus S dash I am choosing as epsilon. Let epsilon equal to S minus S dash. For this epsilon, the condition 2 is true, no? So x is greater than S minus epsilon. That implies x is greater than S minus. Instead of epsilon, you substitute S minus S dash. So x is greater than SS get cancelled S dash. This means what? There exists an x in the set which is greater than S dash. That means this S dash is not an upper bound. Okay, there is an element which is bigger than this S dash, no? Therefore, this is not an upper bound. If this is not an upper bound, what do you conclude? Any real number S dash, if you take less than S, that cannot be an upper bound. Okay, right? So, that means what? S is the least upper bound. Okay, so the theorem is proved. In the same way, we have characterization for infimum also. So, if T is an infimum, if and only if x is greater than or equal to T for all x belongs to S, and if epsilon is a positive real number, then there exists some x for which x is less than T plus epsilon. The proof is similar to the previous one. Okay, that's all. Thank you.